3I Atlas is the name given to the third known interstellar object, or ISO, that has entered our solar system. That's what 3I stands for, Third Interstellar. The first such object was 1I Oumuamua, discovered in 2017, and the second was 2I Borisov in 2019. Because of their hyperbolic orbits, these first two objects are already far outside the inner solar system by now, and they'll likely never return. 3I Atlas is on the same type of trajectory, so we only have a very limited time, probably just over half a year in total, to study it. ISOs are a relatively rare thing to be spotted, as such astronomers from around the world are focusing their efforts on studying it while we can. So, what have we learned about it thus far? That's what this video is going to answer. Let's get into it. 3I Atlas was first observed on July 1st, 2025 by NASA's ATLAS telescope, hence the second half of its name. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, and it does exactly what that name implies. It's an automated system that spots asteroids and comets that might be a threat to Earth. Don't worry though, we're not in any danger. Very soon, astronomers realized that 3I Atlas was an ISO due to its hyperbolic trajectory, which was calculated through observations by both professional and amateur astronomers. These calculations also confirmed that it wouldn't get very close to Earth after all. Since then, telescopes the world over have been trained on it, and even our space telescopes like Hubble and James Webb have been observing it, although we still have to wait a while longer for data from the latter to be released. So, what have we learned by observing it so far? Well, it's a comet with typical cometary properties for one. To all the people out there saying, "We don't know what it is yet," stop it. We do know. Those who say otherwise are lying to you and keeping some very simple truth from you. Let me clear that up for you. How large is 3I Atlas? First off, some terminology. A comet consists of a nucleus, a coma, and typically two tails, though some comets without tails have also been observed. Nucleus and coma aren't negotiable though. The nucleus is a comet's solid core, whereas the coma is a sort of atmosphere that surrounds it. It's not really an atmosphere though, since a comet doesn't have enough mass to keep one. It's mostly ice and dust which comes loose because the heat of the sun starts to boil the volatile materials inside the nucleus, like water ice for example. This usually happens at a distance of 3 to 4 AU from the sun, which is perfectly in line with our observations of 3I Atlas. You can very easily see the coma here. This paper here puts the radius of the nucleus at approximately 2.8 kilometers, so 5.6 kilometers in diameter, but with a theoretical minimum of 0.32 kilometers in diameter. The authors state that it is much more likely to be on the smaller side, but it's hard to tell because of the coma. By the way, why would a spaceship produce a coma? Who knows? For comparison, 1I Oumuamua and 2I Borisov had a radius of 0.1 and 0.4 kilometers respectively. Now, usually the two tails of a comet are 1, the ion tail, which points directly away from the sun. It consists of the atoms ionized through the sun's radiation, and 2, the dust tail, which falls off because of the sublimating ice and it just sort of trails behind it. Here, however, we can see sun-facing emissions. So if you're wondering what that's about, it's again just dust that is thrown away from the comet because the ice below it starts to sublimate and kind of poof away. Naturally, the side facing the sun is the one most affected by this. Moving on to 3I Atlas's age now, you might be wondering, how can we possibly deduce the age of an interstellar comet? And it is pretty tricky, but we can make an educated guess. Here's how it works. It all has to do with kinematics. I won't get into too much detail, but I will link all of the papers below if you want to do some reading of your own. Essentially, we can measure 3I Atlas's orbital parameters and also its speed. Also, the previous two interstellar comets both entered from the celestial northern hemisphere, whereas 3I Atlas came from the south. The celestial hemispheres are defined by the way the solar system travels in the galactic plane, with the northern hemisphere pointing in the direction of travel. 3I Atlas's entry speed into the solar system is much higher than that of the previous two interstellar comets. Oumuamua had an entry speed of 26 kilometers per second, Borisov traveled at 32 kilometers per second, but Atlas traveled at 58 kilometers per second. Using all of this data, we can deduce the likely origin of these comets. Atlas seems to come from the galactic center. Here's the calculated orbit of Atlas around the Milky Way in red and the solar systems in yellow. This also shows that it belongs to the thick disk population, whereas we belong to the thin disk. The stars in those regions are generally a lot older, and that's what we base our age estimates on. These older stars also exhibit much lower levels of heavy elements than newer stars like our Sun, so a spectroscopic analysis of Atlas can help us to confirm or deny this. More on that in a bit. Now, an initial study in July said, with 68% confidence, that Atlas is between 7.6 billion and 14 billion years old. A newer analysis puts its age somewhere between 3 to 11 billion years old. Our solar system is only 4.6 billion years old, so Atlas might well be older. It's also way older than the previous two ISOs. In this graphic, you can see the probability distributions of the ages of all three objects, with Oumuamua in blue, Borisov in pink, and 3I Atlas in orange. Their statistical median ages are 1.2 billion years, 4.8 billion years, and 6.9 billion years respectively. Now, as for the spectroscopic analysis, one has already been done, but since Atlas at that point was still at 4.4 AU from the Sun, no clear absorption features could be made out. Very quickly, a spectroscopic analysis works because different elements absorb different wavelengths of light, so if certain wavelengths are missing, we can infer the existence of the corresponding elements. There was a very shallow depression noted here between 6,000 and 7,000 angstrom, which would indicate the presence of hydrogen. Iron, notably, does not absorb light in this wavelength, which would be in line with what we talked about earlier concerning Atlas's origin. The paper, however, is very cautious in saying this. More spectroscopic analyses will have to be made once the comet is a little closer. As for the color, it's been noted that it seems reddish, and this has been confirmed by initial photometric observations. This resembles D-type asteroids, which are generally found on the outer edges of our solar system. It also lines up with the other ISOs, which had very similar photometric features. Lastly, I want to quickly touch on this paper written by him who shall not be named, which calculated the trajectories and possible origins of our three known ISOs. To sum it up, it basically confirms what we already know about the most likely origins and ages of the ISOs, stating their ages as 1 billion years, 3.8 billion years, and 9.6 billion years. It also confirms the thick disk source for 3I Atlas. I already made a short about this paper and my thoughts on it, so why don't you go check that out. Okay, that should do it for this time here on Awful Astronomy. If you stuck around this long, I want to say a huge thanks, and I hope you learned something today. Please, while you're here, give me a like, leave a comment, and subscribe if you want to see more videos like this one. Also, if you have any suggestions for what to cover next, please leave them down in the comments, and I'll be sure to add it to my list of topics. Alright friends, remember that you are all beautiful, lovely, and deserve to be happy. Until next time, stay stellar.